Right, my name is Kyle Campbell. My presentation is on applications of machine learning in digital communications and signal processing, specifically optical communications, which is kind of my focus in my career. I wanted to make this presentation a little bit more conversational. So if you have any questions about you require further clarification or just any additional details that pique your interest, don't wait until the end. Just ask whenever. Feel free to interrupt because I kind of left room in my presentation for there to be a little bit of talking anyway. First off, what do I do? I'm a hardware engineer at Effect Photonics. First, I joined the Viasat DSP team, digital signal processing team, in April of 2020, and they're based in Cleveland. In March of 2022, our team, including myself, was offered to work at Effect Photonics. Effect Photonics is a startup based out of Eindhoven in the Netherlands. Eindhoven is actually where Philips is headquartered and started, so it's kind of like a tech hub up in the Netherlands. Our team makes DSP ASICs for coherent optical transceivers. Effect as a whole makes what are called direct detect and coherent pluggable transceivers, which I will describe more. These pluggable transceivers, basically on this side is kind of like an Ethernet connection, and on this side is actually where there are two fiber optic lines. And this is, in essence, the backbone of the internet. All the data centers and all the different gateways and things use fiber optic in order to communicate because it's by far the highest bandwidth sort of way of doing digital communications. And every single bit you receive today goes through fiber, whether it's through your cell phone, cable internet, whatever. So the most simple version of modulating and demodulating digital data through optical fiber is through what's called direct detection. This is kind of what you'd imagine if you were to take a laser pointer and just kind of turn it on and off at a specific data rate. It's just capturing the amplitude of it. In the simplest form, it's just capturing whether it's basically low or high and doing some kind of simple thresholding. This actually works quite well up to certain bandwidths and distances because optical fiber, like laser light, just has a very high frequency, so it doesn't require necessarily more advanced modulation techniques that you might see in RF. One issue with this is that the receiver isn't able to get the phase information from the signal, so it's only able to capture the power or amplitude of the signal. And this puts a limitation on the kind of post-processing that can be done on the received signal because it simply doesn't have all the information that was available in the channel itself. The biggest thing is that there is a very important concept called chromatic dispersion, and this is the reason that rainbows exist and all kinds of stuff like that. Basically, different frequencies of light travel at different speeds through a medium, and that over the distances that we talk about in optical fibers causes pretty significant distortion of the received signal. And you can see an example of this here, where the original signal might be some kind of very simple switched square wave, but the pulse actually gets spread out in time as it goes through chromatic dispersion. As it becomes more and more distant from the source, it spreads more until they actually start to interfere. And of course, you can imagine when they start to interfere to the point that they're kind of significantly overlapping, that would cause bit errors. So that places kind of a fundamental limit on direct detection, at least through the sort of standard means that you would expect. This slide's a bit chaotic, so mind. The second and more complicated and more interesting version of digital modulation, optical modulation specifically, is coherent detection, where to start you have bits and you place those bits, you map them into symbols, in this case on the complex plane. And the way, if you learned in a digital communications class or elsewhere, that you can transmit data as you have an in phase and a quadrature component. One waveform is modulated with, say, a cosine wave, and the other waveform is modulated with a sine wave. They're out of phase with each other, and they actually are sort of orthogonal. So you're able to map, in this case, which is called a 16 quadrature amplitude modulation technique. You're able to map 4 bits to a single symbol, so you can send every sample 4 bits of information. Not only that, but you actually have 2 orthogonal polarizations in light, including in laser light. So you can actually double the bandwidth by utilizing that, by having horizontal and vertical polarizations kind of operating over the same fiber independently of one another. And this diagram here shows that in a little bit more complexity, where you can see 2 separate modules that are taking I data and Q data, converting it from digital to analog, modulating it with a sine and cosine tunable laser in this case. These tunable lasers are horizontally and vertically polarized, so they are combined together in this polarization beam coordinator, or combiner, sorry. It runs through the optical fiber, which is where all the impairments happen, or most of them really. Then they're split at the receiving end, and then they are demodulated using, again, tunable lasers, or a single tunable laser with a 90-degree phase shift, and then they are digitized, and then it reaches the DSP, and this is actually where I do my work. So the received signal in the DSP is, you could think of it as every sample you have 4 numbers, and those numbers are quantized. They might be like 8 bits, 6 bits, depends on the use case. So not only are they're not floating points, they don't have infinite precision, they have a very finite precision. So there is a very real sort of concern of quantization noise, and that can definitely cause effects downstream. So when you actually have a signal that's transmitted and received in the DSP, it might look something like this. It should look like this. Ideally, it should be 16 perfect points, which is what it would be if it was an ideal channel with no noise. What's received is this, which the most clear thing is it's circular, it's spread out. Basically, there is some kind of frequency offset that it's smearing the data. And that can be corrected by estimating and correcting for the frequency offset, which is done in the DSP. Some important metrics that actually are very important, of course, for machine learning, because you need some kind of metric, some kind of cost function to guide the process, are twofold. There's OSNR, optical signal to noise ratio. This is more or less what you learned in some of your other undergrad classes, that you have a signal and a noise, and you can compute the power of both of those and divide them, and you can do the log as well. One thing that's kind of important is that you don't necessarily have the noise power on hand. You have to estimate it normally by comparing the transmitted and received symbols, and from that you can get the MSE and compare that to the signal power. Then there's the bit error rate, and this is kind of the really useful, important metric. It's exactly what it says it is. It's basically just how many of the bits that were received are different than the ones that are transmitted. Of course, that means that you have to know what the transmitted ones are, but when you're doing simulations or running lab tests, you have that information. This one is a little bit more difficult, because even if you have this constellation right here, you don't necessarily get the bit error rate, because you need to decode the data farther by sort of, the most simple case is by drawing a grid like this and doing a simple detection. It's basically a 16 hypothesis testing. And you also have to know where the bits should be. So it's not just, you have to know whether it should be here or here or wherever. So you do, again, need the received data, and you need to correctly just basically do everything through the process in order to get to this point. And one more thing is that the ESNO and BER are related pretty intimately. If you at least assume Gaussian noise, which isn't an unreasonable assumption, you can calculate what the theoretical BER could be given some signal to noise ratio. In that formula, it shows EB, which is the bit energy to noise ratio. They're very simple computations. It's just proportional to the number of bits per symbol. This diagram shows a little bit more within the DSP. As I mentioned, you have the analog to digital conversion, and the actual DSP is right here. There are several sort of processes in sequence that happen, and each of them are doing different corrections for the impairments. The really important ones are, I would say, this one and this one. So wavelength dispersion, or chromatic dispersion, is doing a correction for the chromatic dispersion of the captured signal in order to basically invert it and undo that effect, which is actually not that difficult. And then nonlinear compensation. There are a lot of different nonlinear effects. The most important one, I would say, is the carrier frequency offset. So the received signal and the transmitted signal don't necessarily have, the laser might not be identical for them. So when you demodulate, they're going to have a slight offset, and that needs to be corrected for in order to actually capture the original data. And there's also an algorithm to estimate and correct for that. Another thing is adaptive equalization. This is the closest thing to machine learning that I see in my day-to-day job. It's basically having a filter, a series of filters that are simply kind of like iteratively kind of computing the residual impairments and correcting for those. And that's kind of more or less the last step before you actually decode. There's a few types of dispersion that I wanted to briefly go into. The top one, modal dispersion, isn't that relevant because a lot of coherent DSPs and optical systems use a single mode, so there is no multi-mode. You just have a single sort of mode of light that is able to propagate. Chromatic dispersion is what is discussed earlier, and this just shows basically two different frequencies will have two different sort of phase offsets or group delays or velocities. And the polarization mode dispersion is an interesting one that basically the horizontal and vertical components can have different speeds because of imperfections in the fiber as it propagates. And that also can be corrected linearly in the adaptive filter. A few more impairments that are worth mentioning. Some of the linear ones are actually created not in the channel, but in the electrical domain itself. So as it gets sort of turned from an optical signal to an electrical one, there are a few different places that you can get these impairments. They are typically corrected first thing once it's received, because you need to do that before you do any frequency offset, because it needs to be in the same frequency as the others. Nonlinear, the frequency offset which I described, that one is pretty straightforward to be estimated or removed. And the phase noise from the RX or TX local oscillator, so we assume that things are additive white Gaussian noise, but the actual local oscillator itself has, a laser isn't perfectly, it's not a perfect sine wave. It has what's called linewidth or phase noise that is mixed in with the received signal. On its own, that's not too bad, but actually it can become worse and become nonlinear when it's either that signal is equalized or in the actual channel itself, there's something called the Kerr effect, which can cause this phase noise to become nonlinear, and that will be described later. As I mentioned, the signal processing that we do is not very machine learning based, at least in my day-to-day job, but there are definitely a lot of applications towards it. Machine learning has a lot of applications for this because you can get the training data just by turning on the receiver. The power consumption from one of these modules is, a lot of it comes from the DSP itself, so if you can utilize machine learning to reduce the power consumption, that would be very, very helpful, because power is everything in this. And as I mentioned, adaptive equalization is something that we use in our day-to-day job. So this is just a little bit more detailed breakdown that I found in the paper. Basically, the top diagram is showing a simple FIR filter. You could think of it as a single layer deep neural network that is simply computing what is called the constant modulus. So you can assume that at least some of the symbols are going to be at a specific distance from the sort of from the origin, and have a filter that is optimized by minimizing the sort of average error of those symbols from the target radius. So what that does is allows you to do adaptive equalization and control the output power, because you can control that radius. And in the bottom one, this thesis actually as well created a simple neural network that uses, instead of a single FIR filter, it uses 2 FIR filters. And the kind of funny thing about this is that in the end of it, they kind of were shown to have more or less identical performance, but the neural network design had a lot more performance usage, resource usage, especially of the DSP blocks in the FPGA. So it kind of shows that machine learning isn't just some hammer that you can hit on anything. Like, it really does require a lot of thought, and it can't just be used to solve every problem out there. One example of a non-machine learning technique that we use in order to correct for chromatic dispersion in a coherent DSP is to basically do an inverse filter of the chromatic dispersion formula, which you can see right here. This is the frequency domain representation. An important point is that it is just applying a phase offset to each frequency. There is no, it's an all-pass filter. It doesn't have any amplitude change. And what you do is you take the data, you find a subset of it, say 512 samples, then you perform an FFT of that, you multiply by this computed reverse channel function, which is parameterized by the length of the line of the, which you can either just know, or you can kind of estimate that, or you can just guess and check and just keep trying different values until you get the right one. And that doesn't change, so it's kind of okay to do that. And then there's the frequency of the tunable laser, which is also known. And then there's a bunch of other constants that are thrown in. And so you multiply that by each of the 512 points, and you do an IFFT, and now you have a signal that has been, has completely, or yeah, it's basically completely corrected for the chromatic dispersion. One issue with this is that the chromatic dispersion and phase noise don't play nicely with each other. Basically, the correction of chromatic dispersion actually exacerbates the phase noise and causes what was sort of a noise along the radius turns into a sort of noise that's more like an additive white Gaussian. And that causes pretty serious issues for higher line widths or higher chromatic dispersion. What this article goes into is quantitating that. It's not actually using any machine learning, but it has this very handy sort of graph that shows, I'll quickly go over this. The OSNR is the signal to noise ratio. In a lab setting, it can be controlled. And it's very useful because you can compare to like the theoretical bounds or compare different sort of operating conditions. And then of course the bit error rate is on the vertical axis. So what you see here is that on the left you have what is the frequency domain equalization, which is here. And you can see a pretty steep drop off, especially for the 400 kilometer case versus the 200 kilometer case. So as the CD increases, it has worse performance. And then on the right, you can see they're kind of on top of each other because they're done using a more typical method. Or this is done using optical dispersion compensation, so you can actually have hardware outside of the DSP that is performing that inverse chromatic dispersion effect instead of doing it inside of the signal processor. And that avoids this issue where the digital compensation of CD actually interacts with phase noise, because it's done before the laser modulates it. This shows a more advanced machine learning technique called kernel least mean squares. And it is a least mean squares algorithm, which is a type of iterative machine learning algorithm, but it is first transforming the input data, meaning the receive symbols into a higher dimensional feature space. In the example of this, it uses something called the Gaussian kernel, which, as far as I'm aware, is actually an infinite dimensional space, but then it somehow finds a subset of that space and uses that to actually create a CD compensation filter that also is able to correct for this nonlinear phase noise, which I described earlier. And what this does, you can compare it to this savory one is more or less similar to the one I described as frequency. So it has a higher bit error rate, and then for the KLMS, it's farther much down here. This back-to-back is basically what would happen if there's no CD at all. All right. This is just a really interesting example of, I would say, more directly applying machine learning principles to coherent modulation. In this case, you have a 64 QAM signal, so it has 64 points. The more symbols you add, the more you have to concern yourself with noise and other impairments, because if you only had 4 symbols here, you have a lot of room of error. But here, especially when you get towards the outer edges, you have some serious likelihood of getting a bit error. And it's non-uniform. You know, in the middle, it's much more easy. And this comes from the nonlinear phase noise that is more or less unavoidable. And what this does in this article is it applies k-means clustering and Gaussian mixture modeling into a pretty typical coherent design in order to create decision boundaries that are a lot more, I would say, they're definitely optimized, but they're definitely nonlinear. So it uses some machine learning to actually create this boundary set. And it improves performance pretty significantly by doing that. Okay, so now we're actually going back to direct detection. What I mentioned earlier about direct detection having limitations and how it can resolve CD, that's not strictly true when you're able to utilize machine learning. Basically, direct detection is taking the signal and only capturing the power, so it's a nonlinear transformation because it's basically squaring the data, or doing the complex conjugate, I suppose. And you still have that amplitude and you can make estimations with that. In this case, the author spent a lot of time basically playing with different setups and created a neural network that has 7 taps and 6 hidden layers, which is all in all pretty simple, and therefore is easily implementable in silicon or in an actual ASIC. And what it shows is that, for instance, with this ANNEAT, which is adaptive neural network, advanced testing, and it goes through the details of how it does that. It's able to show that without an equalizer, which is typically what you would see, you have basically terrible performance whenever you, in the CD range that it's showing here, I think which is 200 kilometers. You have 200 kilometers. And then with this, it is much closer to the actual back-to-back. So it's almost, it's much closer to if it had no CD at all. So this allows you to have direct detection at a much larger distance than what was previously possible. This is only able to be done using machine learning because this is a nonlinear function that it has to be estimating and inverting. And that just simply can't be done using linear means. And it really can't be done sort of with more simpler estimation. And this one, which I believe is my last slide, is a really, really interesting development that I saw. And there was even a sort of follow-up article to this one that ups the ante, but I wasn't able to get access to that, so this will do. Basically, they were able to use these micro-ring resonators, which are shown here. I think there's 4 of them, though I only see 3 in the figure. And these micro-ring resonators are used as photonic, what are they called? Photonic neural networks. So each of these kind of represents a neuron. a feed-forward neuron, and it's able to be trained and controlled some of its parameters related to its coupling and other things. It's a nonlinear system, so it can do really interesting things with that. And what this does is once it is trained, it is able to, in essence, do this, but in photonic neural networks, and is a much, much lower power, and could be its own discrete device that is able to compensate for CD before it even reaches the receiver, and at a very low power. So this is a very interesting development. Like I said, there was a subsequent article that went to 8 of these microring resonators, and the performance was even better. And it was still, a fraction of the power. So this is something that really may make direct detection more of a viable option, because it previously had been limited in data and range because of those limitations I mentioned earlier. And aside from that, these are just all the references that I had in the slides, and that is all.
Very interesting. So the last one is that the last reference, or you just mentioned,
yes.
or the second?
Second to last.
Okay.
And I'd be happy if you could find a way to access this article, but it was by the same authors. And I could even send you the link to it, but it was from SPIE, and it was only posted like 2 weeks ago, and it seemed really interesting. I read the abstract. I didn't really care to share the abstract.
And it's
because
not
it was
accessible by the libraries?
I tried to log in using the institution, and it kind of kicked me out. I can't really describe it. It just didn't. It didn't let me log in. Basically, you might be able to log in, honestly. So.
Well, I mean, if you contact the library, they should be able to. You should either have direct access, or if you don't, they should be able to get it for you.
That's true. Yeah, I tried to look through the catalog, the library catalog, but I think it's just because it's such a recent article. I was actually able to request it from the authors.
It should be there.
Yeah,
If
sure.
it's a recent article, it should be there, but if Ohio State doesn't subscribe to that, then they should be able to get it to you.
Yeah.
When you get it, send it to me.
Yeah, I very much will. I'll probably stop by the library, honestly, after this, because it really it kind of is a great top off to this, because you're actually using photonics to create neural networks for photonic impairments. It's just very recursive. It's super interesting. So I'm really interested in the development of this.
This
So,
is kind of the next generation of things, right? So
Yeah.
if you can create the learning elements in the same domain as you can fix, that automatically brings the efficiency of your
absolutely.
So it's very interesting.
I will mention the reason that the DSPs use so much power compared to the rest of the chip is just a natural consequence of how transistors function. Every single time they switch, they use some amount of power, and when you have billions of those things operating at basically full capacity the entire time it's running, it just naturally uses a lot of power. And something that you have is 3 or 5 watts, which doesn't sound like much, but then you have entire data centers using that, and it very quickly adds up.